So, good evening. Today we will be starting with the new chapter, digital filters, and we will be basically discussing about the FIR filters in this chapter. Okay. So, these are the course outcomes which you should be knowing by this time. So, when we talk about the digital filters, so till now we have already discussed that the digital filters they are basically represented with the transfer function which is given by xz equals to yz by x of z. Okay, I need not to discuss about all these things, how this transfer function comes and what is the relationship. We have already discussed many a times. Okay. Now, when we talk about this transfer function can be designed in two ways. The first one is the in this way where hz is equal to summation of I equals to 0 to n hi z to the minus I and so on. So if you see over here, there are no denominator components. And this type of filter, they are regarded as finite impulse response filter. Okay? And they're also regarded as non-recursive filters. Okay, so what is the specialty of this filter? The specialty of this filter is that non-recursive means there is no feedback loop. Okay, while designing the filter there will be no feedback loop. Okay, so what do you mean by feedback loop? So none of the outputs, previous outputs, it will be taken into consideration while calculating the current output. Okay. So it will, the FIR filters, they will only be taking up present and past inputs, and based on the present and the past inputs, it will give you the current output. Okay. So on the other hand, what happens is that if you look into the other type of the filter, it is called the IAR filter, and it is also regarded as the recursive filter. And if you look into the transfer function equations, there are two polynomials, one in the numerator and one in the denominator. Okay. So again, another important thing, if you remember correctly, in the pre-midsem one of the classes, I told you the difference between the FIR and IIR filters. So, what is the from where this name comes? The name comes from the fact that in FIR filter, the impulse responses they are finite in nature. That means after particular number of outputs, the output will be 0. Okay. How? In the case of IR filter, this is not the case. You will be getting the outputs once you what you call supply the system with an impulse input. Okay, so you will be getting an infinite number of series. In the case of FIR filters, you will be getting a finite number of series, whereas in the infinite impulse response filters, you will be getting infinite number of the output points. Okay. So, in this chapter, we will mainly be discussing about the FIR filter. Okay. So, to make our life easy, what we will be doing, we will be taking a transfer function wherein I have truncated the coefficients to 3. Okay. So, you can increase it to n number of things also, but for our easy understanding, I have taken only 3 filter coefficients. So let us take this transfer function to be 1 equals z equals to 1 plus 4 of z inverse plus 4 of z to the minus 2, and then you can represent this equation as 1 plus 2 z inverse whole square, right? So we get z equals to 1 plus 2 z inverse multiplied by 1 plus 2 z inverse, then multiply and divide both the numerator and denominator with z to the power minus 2, and when you do that, you get in the numerator z plus 2 multiplied by z plus 2, and in the denominator you get z square. Okay, so now we have to determine the location of the poles and the zeros. So where are the poles? So for determining the poles, we know that denominator we have to equate it with to 0. So z square equal to 0, that means z will be at 0. Since it is z square, that means there are two poles at the origin. On the other hand, if you look into the numerator, we are having z plus 2 multiplied by z plus 2. That means we are having two zeros at z equals to minus 2. Now, since in the transfer function, we are only having the numerator component, so when we try to simplify that and try to get the location of the poles and the zeros, so what happens? In the denominator, you will always be having a factor z to the power n. Okay, you will be having a factor z to the power n, and when we try to equate it to 0, you will always get n number of poles at the origin. Okay, so if you look into this case, so what is happening? The poles are always at the origin. Okay, so the construction of the FIR filter is such that you will be having poles always at the origin. And what does this mean? This means that the FIR filters, they are inherently stable. You cannot make an unstable FIR filter. Okay, why that is so? Because from our filter designing aspect, we know that the pole should always be within the unit circle and the origin is within the unit circle. Okay. So herein I have given you the explanation of this one, what I have told. So any digital filters transfer function, they can be given with xz equals to yz by xz, and they can help us in classifying the digital filters into two types: FIR filters. So FIR filters, which means a finite impulse response filter, and they are regarded as the non-recursive filters, and their equation it is given by this one. And similarly, we have having the IR filter, which are regarded as the recursive filters, and their equation is given by this equation. And then we have discussed about this. We have taken an example of FIR filter, and we have looked into uh, why this FIR filters, they are inherently stable in nature. Now let us take that example and then try to implement the filter. Okay, so we have already discussed about the direct implementation, right? Direct form implementation we have already discussed, and you can look over here, right? So I think you should be able to make it, right? So let us discuss about the process, what is happening over here. So in this exit, we are having this one, this transfer function. Then we are breaking the exit into the component yz by xz. Then we are taking this exit on the right hand side and multiplying with the right hand side portion, and we are getting this equation. And if we perform the inverse Z transform, we will be getting the difference equation. Okay. Now from this equation, we can find out the signal flow graph also. This is called the signal flow graph. So and this is called the realization. Okay. So both are the same. So basically they are the two sides of a single coin. Okay. Either you can implement the filter in this fashion, or you can draw the signal flow graph, show how the signal components, they are uh, what you call they are migrating within the architecture. Okay. So let's say let's find out the impulse response So when we have this impulse, input impulse, which is nothing but delta n equals to 1, 0, 0, 0. So that means our exit is equal to 1 and followed by zeros, right? And so on. So here at capital A position, at n equals to 0, we will be having 1, and this one it will be coming to the D, okay? And at location B and C, what is happening? No values, because they are taking, B is taking value from the previous instance and C is taking value from the 2 times of previous instance, okay? So the immediate previous instance and 2 times of the previous instance, those are 0. So from A we will be getting 1 and B will be having 0, C we are having 0. So D is basically the output from this A plus B multiplied by 4 plus C multiplied by 4. In this way we will be having this D addition of these 3 components. So B and C are 0, so we are having B equals to 1 at n equals to 0. Okay. Then what is happening? So A is becoming 0. Okay. So A is having 0. So in the previous instance B is having 1, because A was being the A value from the previous instance, it was stored in this Z inverse. Okay. So that is being released in the second instance. So B gets 1, B multiplied by 1, it becomes 4. Okay. So it comes to the D. So from C we are getting 0, from A we are getting 0, so D becomes 4. Okay. So in the next instance at n equals to 2, what we will be having? This 1 will be released from here. Okay. So we will be getting 1, whereas at A we will be having 0, at B we will be having 0, at C we will be having 1, 1 multiplied by 4, it goes to the D and we get 4, and thereafter all the values will be 0. Okay. So once we get this yz equals to this one, so if you perform the z transform, get back the original transform function. Okay. So if you are provided with the transfer function, you should be able to determine the impulse response of the system. Okay. It is nothing but the filter coefficients. Okay. It is nothing but the filter coefficients. So if I give you a 1 mark question, so it will be a direct answer. So the impulse response, that means Hn of this filter, it is equals to 1, 4. Okay. Am I clear? So this is the signal graph. So if you see the adders, they have been replaced with some nodes, these dots. Okay. And these multipliers, they are replaced with arrows. This is the only difference. So the nodes means addition and these arrows means multiplication. So herein the same thing has been explained. We are having this xz equals to this transfer function we are having. So then we can break it down into yz and xz, and from there we can simplify the equation, and from there we can find out the difference equation. So this is the difference equation, and then from there we can go for the realization. First we went for the direct form realization, then we also went for the signal flow graph, okay, which is another way and a compact way to represent the same structure, and it uses nodes and directed branches to show the flow of signal. Okay. Then we also found out the impulse response for that. Now if you look into the transfer function, so what is happening in the transfer function? We saw that we could have simplified the transfer function in the form of capital A square, where capital A is 1 plus 2 z inverse whole square. Okay, so we can write it in this fashion. Again, we can write xz in this fashion. So you can bring this xz here. Okay, xz multiplied by this one multiplied by this one, right? That will be your yz. Now, when we have a multiplier in between, so what is happening? If you see, this is subsystem, say A1, A1, A2. Say this is capital A1 and this is capital A2. So the output of the A1 is taken and fed into the A2. Okay. So input goes to A1 and then it goes to A2. And this kind of system representation or implementation, it is called cascading form of realization, okay, or cascade form of realization. First one is the direct one, where we are directly implementing, so there are no subsystems. However, if we can break it down into several subsystems, then we can implement the system by cascade form realization. Okay. Now again, we can find out the output of this system. Okay, and you will be finding that it is the same. Okay, so please do this thing. Okay, let me finish this lecture and then you can solve this one, how to calculate the impulse response using the cascading system. So cascade realization, we have already discussed about this and I have just given you the explanation over here. Now when we design any kind of FIR filters, you have to have certain considerations in mind. Okay, the first consideration is the magnitude response. Second is direct design process. Third is separate design of magnitude and phase. Fourth is linear phase, and then we have this design method. So there are no specific rules over here while designing the FIR filters. And lastly, we have filter characteristics versus the complexity. So these are the key considerations that has to be kept in mind. So in a snapshot, I have given to you in a single slide, but from the next slide onwards, we'll be discussing about this. Okay. So in the magnitude response, what you have to keep it in mind. So when we talk about the magnitude response, we should keep it in mind that the ideal goal for the passband is a magnitude response of 1. That means modulus of h of omega should be equals to 1. Okay. So what does this implies or signifies? This implies that the magnitude of the output signal's frequency components equals to that of the this output component. Why it is coming? We know that h of omega, it is equal to y of omega divided by x of omega. So, but we are trying to keep it as equal to 1. So what does that mean? This x will go on the right hand side and we will get modulus of y of omega equals to modulus of h of x of omega. And what does this mean? Whatever will be the gain or the amplitude response of the input values, will be getting the same thing at the output. That means there will be no change in the amplitude response in the pass band. Okay, in the pass band. Okay. So over here, what are the key players? The key players include the input signal x of omega, the system h of omega, and the output signal y of omega. And the fundamental relationship, when we are assuming that the magnitude response will be 1, by implying this, what we are doing, we are getting into this equation, and since we are considering that h of omega it is equal to 1, by this method we are saying that modulus of y of omega will be equals to modulus of x of omega. Okay, so when we talk about this magnitude response, there can be several what you call permutations and combinations. So if the modulus of h of omega it is greater than 1, then the filter amplifies the frequency. When it is less than 1, the filter reduces the strength of that particular frequency. Okay. When modulus of h of omega is equal to 1, the filter lets the frequency pass through completely unchanged within the passband region. Okay? And modulus of h of omega, if it is 0, the filter completely blocks that frequency. Okay? So, what we are doing while designing the filter, because what is the main function of a filter? The main function of a filter is to either pass or not to pass the some of the frequency component. Okay, so it depending upon the nature of the filter, it will pass the frequency components within the passband region, and it will stop the frequency components that fall in the stop band region. Okay, so as we put it all together, we got this equation, and it means that for every frequency within the passband, the magnitude of the output signal is identical to the magnitude of the input signal. That means there is no loss of signal strength within the passband region. The next thing is the direct design process. Okay, what does this mean? So this means when we talk about the IIR filter, in most of the digital signal processing books, you will find after giving the basics, they get into the IIR filter. Why? I will also tell the reason. The reason is that the IIR filter designing, it was what you call, it came first. Okay, why it came first? Because the uh, designing process of the IF filter, it is basically it is being derived from the analog filter domain. Okay, so we have a rich knowledge about the analog frequency, and what we are doing analog filters, and what we are doing, we are trying to embed the same with the IF filters. Okay, and then they get into the FIR filter because it came at a later stage. But in this class, as you will find, many of the students they are from different backgrounds, and all of them they don't have an understanding about the basic filtering techniques and all these things. Understanding the FIR filters and implementation of that, that gives them a better understanding to get into the IR filter design. Okay, so that's why I teach it in a reverse way. Okay, so this is what it tells is that when we talk about these fire filters, we are directly taking or designing the filters from the knowledge of what we want from the filter. Okay, so that's why I told you you need to understand how the low pass filter can be designed, how the high pass filters can be designed. So that was my basic idea to make you understand how the placement of the poles and the zeros they play an important role, and how the placement of these poles and the zeros they affect the amplitude response. Okay, now once you are having the understanding of this one, it will be easier for you to design the FIR filter, and then we can move towards the IR filter. Okay, so if you see, the FIR filters are typically designed directly in the digital domain, whereas IR filters, this is contrasted with the IR filter design, which often starts with an analog low pass filter prototype and uses frequency transformations to obtain the desired filter type. Okay, band pass filter, high pass filter, band reject filter, or whatever the filter you want to design. Okay, on the other hand, in the FIR filter, we are just placing the poles and the zeros as per our convenience, and then we are able to manipulate the response. And when I say the poles and the zeros, we know the position of the poles. The position of the poles for FIR filters is always at the origin. Okay, so as I told you, FIR filters are built from the scratch in the digital world, while FIR filters are adapted from the pre-existing analog filters. Okay, so designing an FIR filter is a direct process that happens entirely within the digital domain. So that makes our life easy. So you start with the desired frequency response specifications like the cutoff frequency, the pass band ripple, the stop band attenuation. So whatever I was telling. So you need to understand what is your requirement. What should be your cutoff frequency? What should be your stop band frequency? After that, you should not get anything. Okay, what should be your pass band ripple? Okay, so all this information, if you are having, then you are good to design a FIR. Okay, so you can think of it as just like as a 3D printing a custom part. Okay, so what we do in 3D printing, we design it on a computer from the ground up to meet our exact needs, and the final product is created directly from the digital blueprint. Okay, so popular direct design methods for FIR filters include windowing method and Parse-Maclean algorithm. So we will be mainly concentrating with the windowing methods, and we will not be going into the Parse-Maclean algorithm, but I will give you an understanding what happens in the Parse-Maclean algorithm, because if you go into that, we will not be having the sufficient time to cover the other parts. So on the other hand, in IR filter, it is basically the indirect method of designing the digital filters. So over here, we start with an analog prototype. Okay, so the design begins with a well understood high performance analog low pass filter such as Butterworth, Chebyshev, and elliptic filters. So these are different types of filter designing methods. So we take up a special class of analog low pass filter, and which serves as the template for us. Okay, and then after we have designed the low pass filter, we then apply various transformations like bilinear transformation method to design the digital filter for specific applications. Okay. It may be high pass filter, band reject filter, whatever. Okay. So why the difference? Okay. This difference exists mainly for historical and mathematical reasons. The theory for designing high quality analog filters is very mature and results in efficient designs, no doubt. The indirect method for IF filters was developed to leverage these powerful analog techniques for digital application, resulting in highly efficient filters that require a much lower order system than an FIR filter for the same sharpness of cutoff. Okay. The trade-off is that IR filters can have non-linear phase, while FIR filters can easily be designed to be perfectly linear phase, which is crucial for applications where preserving the signal's waveform, shape, and it is important. Okay. So what does this say? So this says if you want to design IR filter, you'll be very comfortable to design it because you already have the template. You take the template, apply some methodical methods, empirical methods, and you will be getting the design filter. Okay, so you will be very comfortable to design it. But the problem is that in IR filter, the amplitude and the phase components, they are interrelated and they are taken or considered at the same time. Okay. Now, because of this reason, if you try to manipulate the amplitude response, your phase response get distorted, and vice versa. If you want to manipulate the phase response, your amplitude response gets distorted. So over there, we come to a trade-off that okay, I want this kind of phase response, and if for maintaining this kind of phase response, if there is some what you call deviations in the amplitude response, I will accept that deviation. Okay, and vice versa. So, what is happening? You yourself are accepting that I am incorporating some what you call discrepancies within the filter signal. Okay. On the other hand, if you see, since it is a complex system, so complex means designing aspect is quite a bit complex. So since it is a complex system, you can uh, play with the roll-off quite easily. Okay, roll-off means the transition from the pass band to the stop band. Okay, in ideal cases, we are having this big filter, pass band, and then suddenly we are having the stop band. But in practical consideration, we cannot have that. So, what happens is that when you are trying to design the filters using the FIR filters, and if you are having small number of zeros, the designing of the filter response or the designing of the filter response, you will be needing a large number of zeros. Okay, you will be needing a large number of zeros. Do not understand? So, what happens is that, let us suppose this is an image. Okay, you have taken, and initially, what I do, I have just segmented this image into four parts. So, if I ask you to recreate this image, so this pixel, it will have some specific average value of all these components. Here, some average value of all the components here also. So, will you be able to get a good quality image? It will appear as pixelated. Okay. Say for example, you are having a 2 megapixel camera. You are taking my image and you are zooming out, say 200%. My full face will be looking as a pixelated thing. But at the same magnification and all the same thing, you take a 50 megapixel camera and you take the image, you may be losing some information, but you will be getting a detailed information. Okay. So similarly, if you see, what I mean to say is that when you are sorry, segmenting this image to small pixels, you are able to recreate an image which is similar to your original image. You're getting my point? Similarly, suppose you want to shape something. So our ideal low pass filter, it looks like this. So how will you shape this filter? How will you shape this response? You need this response, right? So how will you shape this response? By placing poles and zeros. But in FIR filter, you do not have poles because poles are at the origin and they will not have any effect onto the amplitude response. Why? 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 Uh-huh. So what? Their origin, so why they will not affect the response, amplitude response? They are in the Z plane. Why? So you are not thinking basically. Why it is not happening like that? This is because how did you calculated the amplitude response? जो लास्ट 4-5 क्लास में एम्पलीट्यूड रिस्पॉन्स करवाया, so how did you calculate that? The answer lies over there. हाँ, तो क्या हो रहा है? What is happening to the distance? जीरो कहाँ से आ रहा है? और same distance everywhere, one, and the value is one. So you are having this zero placed some distance you are getting, whatever the magnitude is being placed or the yeah, modified, it is due to the placement of the zeros. And poles, since they are sitting at the origin, the distance is one to each and every frequency component, so they are not playing any role over there, right? So since they are not playing any role, we have to place the zeros such a way such that we are trying to emulate this brick response, brick BRICK, क्योंकि ये brick response or the ideal response. Okay, ideal responses, they are also regarded as the brick response because they appear as completely rectangular in shape. Okay, but in practical consideration this does not happen. So if I have to place one or two zeros, say for example, I am just giving you an example. Okay, so at some particular frequencies, if I place a zero like this or like this or like this, so if I do not increase the number of the zeros, I will not be able to emulate this response, this brick response. Okay, I have to manipulate the frequency responses that it is similar to this brick response. It will never be equal, but it has to be similar. So what I have to do? I have to place a lot of zeros because poles are out of what? Out of sync. They cannot do anything. Okay, okay. So they cannot do anything, but they can. I will come to the phase later on. So we are only left with the zeros. So by just by placing the zeros, you have to uh, shape the yeah, filter response. Okay, you can think of it in these family cases. So if you have both the parents, raising a child become easy. If someone is a single parent with a single mother or a single father, then raising the child becomes or shaping the child becomes a bit difficult. So in the same way over here also, the poles and the zeros, they are the parents. And if you have to shape the frequency response, you need the participation from both of them so that you can shape it in a proper way. But that is only available in the IR filter. In FIR filter, we are only having a single parent, that is the zero. Okay? Yeah. So since we only have a zero, it has an additional advantage. What is the additional advantage? The additional advantage is that we can have a perfect linear phase. We can have a perfect linear phase. That will be coming a bit later. Now, third is separate design of magnitude and phase. A key advantage of FIR filters is that the magnitude and the phase components of the system can be designed and controlled individually and separately. Okay? Individually and separately. That we will be seeing while we will be designing the FIR filters. Okay? So, we know what is the magnitude. Okay, so it is the strength of a signal at a particular frequency. Phase, it is basically the alignment of that of a particular frequency in a given waveform at a particular frequency. Okay. So FIR advantage, it gives us an independent control. I hope all of you know about the magnitude and the phases, right? It is a basic mathematics thing. So we having this independent control, we have this magnitude response, we have this phase response. Okay, So what is phase response? How to time align the frequency components. Magnitude is what frequencies to keep or reject. Okay. So the most important result of this separation is the ability to easily design filters with perfectly linear phase. So a linear phase response means that all frequencies are delayed by the exact same amount of time. Okay. So linear phase means all frequencies are delayed by the exact same amount of time. This is incredibly desirable because it preserves the original shape of the signal, okay, preventing what is known as phase distortion. So linear phase filter, you keep this in mind. Okay. So there is something linear component coming. Okay, that I will be discussing a bit later. So this kind of linear phase filters, they are very much important in signal processing, including the audio signal processing, biomedical signal processing, and data communication. Okay. So what does this mean? This means that suppose you are having an ECG signal. Okay. So what do you mean by phase? Phase means delaying of the frequency component, either they are delayed or not delayed, whatever. Now, if you are having the ECG signal, and if there is a distortion, phase distortion, that means some of the frequency components, they will be delayed higher and some they will not be delayed to the same extent. So what will happen? So in the time domain, what will happen? Some frequency will be there and the other frequency will come up and they will be adding up. So there will be a complete change in the envelope of the signal. अगर आप ECG signal को if you consider that as an envelope, because within that ECG signal, as we all know, that we are having frequency component of 0.5 hertz to 120 hertz. So there are several sinusoidal signals. So one of the signal is delayed, another is not delayed, or what is happening? So what is happening at a particular point, you will be having different frequency components all together. So they can add up. So due to that add up, you will be having a distortion of the signal. Okay? You will be having a distortion of the signal, and that is called the phase distortion. Okay? So in contrast, for IR filters, the magnitude and phase responses are tightly linked. Okay, and hence we do not get this advantage in FIR IR filter. In FIR filter, we can treat the magnitude response and the phase response separately, and we can create linear phase responses. However, this is not possible in the IR filter because there is a and what do you call, both the zeros and these poles, they come into effect, and these phase and the amplitude response, they are tightly linked. Now we will come to this linear phase. So what does this mean? This means, if you see, the FIR response can be easily designed to have a linear phase response that we already discussed. The frequency response of FIR filter is given by h omega equals to capital of M multiplied by e to the power j omega n. Okay, where phase angle of h of omega, it is given by theta omega, which is equal to minus of omega n. So this minus of omega n j theta. Okay, amplitude response is separate, phase component is separate. So we have been able to separate the magnitude response and the phase response. That is the first thing. Okay. Then if you look into the phase, we get phase of h of omega, it is equal to nothing but theta omega equals to minus of omega n, which is a linear function of frequency omega. Okay, so you can think of it as y equals to mx plus c. The c component is 0 and we are having this mx, and theta omega is your y. Theta omega is a phase response, phase with respect to the frequency. So it is forming a linear equation, and hence it is called the linear phase response. Okay. So due to this relationship, what we get two parameters. The first parameter is the group delay, okay, and the second parameter is the phase delay. Okay. Phase delay is all about the deviation among the singular frequency components. Okay, singular frequency components. On the other hand, group delay means uh, it basically helps us to analyze the envelope or the total shape of the curves. Okay, group delay means the total shape. It helps us to analyze the total or the overall shape of the curve. Okay, so we want to see whether there are any distortion or not in the overall shape of the curve. Whereas in the time delay or the group delay, this phase delay, we are basically interested in the delay in the individual frequency component. Okay, in either of this case, what happens is that there is a constant delay for all frequencies, which prevents the phase distortion. Okay, if you see tau g, then tau p, which is the phase delay, it is also n. Okay, so as I was telling you, n is the magnitude response, e to the power j omega n, it is the phase response, and in the linear phase we are having this equation, and this equation can be treated with this linear equation. And if you see, we can cause it as a linear phase response because phase will vary in a linear fashion. And how it will vary, we will be seeing that at a bit later. So in this phase delay, this is the time delay experienced by each individual frequency component of the signal. Okay, and tau p, it is given by minus of theta omega by omega. Now if you replace this theta omega with, what was theta omega? Theta omega was equal to minus of omega n. So if you place minus of omega n divided by omega, this cancels out, this minus minus it gets positive and we get n. Okay. In the case of group delay, we get minus of d theta by d omega, which is equal to minus of omega n by d omega, माइनस बाहर आ गया प्लस हो गया एंड डी ओमेगा बाई ओमेगा is here, n is not having this differential dn we are not having, so this n is basically a constant, so we get this n. So in a linear phase system, we have both the phase delay and the group delay, which are constant, and this n, it is basically related with the length or the order of the filter. Okay, length of the filter or the order of the filter. Okay. So the critical implication, there will be no phase distortion. Okay, there will be no phase distortion. Both the phase delay and group delay are equal to a constant value n. This means that every frequency component of the input signal is delayed by the exact amount of the time as it passes through the filter, and this means there will be no distortion in the signal component, and this is of utmost importance. मान लो आपका आपने एक फिल्टर डिजाइन किया एंड इफ इट इज शोइंग फेज डिस्टॉर्शन, आपका ईसीजी का जो फिल्टर का जो ईसीजी सिग्नल का जो कैरेक्टरिस्टिक्स है, इट विल बी टोटली गॉन. So how will you analyze the signal? It is not possible to analyze the signal then, right? So hence we need a system where there is a zero phase distortion, and that can be achieved using the FIR filters. Okay? The impact of the signals. So as I already told you, phase delay, it is affecting the individual frequency components, and over here modulation of the signal. So these are some of the differences between differences means comparison between the phase delay and the group delay. Now here, if you come, let us take an example: sine of 2 pi f1t. Okay, we are having sine of 2 pi f1t. Now, if I delay this signal by tau time, okay, tau is a time delay factor. Okay, so it becomes my original signal. It becomes 2 pi f1 t minus tau. So what happens if my signal was starting from here? Now it starts from the point, right? Now what is happening? If you look, go back and try to come back to the origin from where the original signal started, we will see we have to go in the negative half. So it is minus of pi by 2. Okay, we are getting into a phase shift of minus of pi by 2. This is the phase shift. So minus of 2 pi f1 tau is equal to minus of pi by 2. Now from here, if you try to calculate tau, it is equal to 4 of f1. Okay, 4 of f1. Now let us take a signal where we have a frequency f2 and f2 is equal to 2 of f1. Frequency double हो गया. Okay, so but the starting point remains the same. So in one cycle we are having basically the two cycles, one complete cycle over here. Okay. Now when we try to go back and try to find out the phase, now the phase is minus pi, right? Now if you again try to find out the tau, it becomes 1 by 4 of f1. Calculate this too. So here what was having for f1, we were having phase of, if we take the modulus, this one thing, modulus of this one, this is pi by 2. If you take f2, we are having pi, right? So if there is no delay, it will be 0. It will be passing through 0. So if you plot a line, it is a linear function. Now are you able to understand what is a linear phase filter? Linear phase filter would be when you vary the frequency, the phase or the delay in the frequency components. So phase delay is for a frequency signal, for a particular frequency signal. Say for example, here we are talking about a particular signal. Okay, but when we talk about the group delay, we are considering all the frequency components together, and when we take the all the frequency components together, they will give you a particular shape. Say for the example of the ECG signal, you are looking into the ECG signal because the different frequency components which are present from 0.5 hertz to 120 hertz, they are combining together. All these frequency components, they are combining together, and then you are getting this ECG signal component, this shape. Now, if you delay some components, what will happen? The shape will be totally distorted. Right? So we do not want to have that. So when we talk about the linear phase component, both these, all the frequency component, they should be delayed at a constant value, and also the group delay, that means all the frequencies as a coherent group, they should also be delayed by a constant value. And this is the importance of the linear phase. Okay? I hope it is clear to you. So the next things we will discuss tomorrow. Already time is over.